All right, so let's see what we can do here. All right, let's do it indeed. All right, so where do you want to start? Okay, so which step, A or C, are you going to introduce your acetaldehyde? A, right? You want to put it on before you try to do anything else, right? We know we're adding an organometallic, and if we tried to add the organometallic first, it would add to the aldehyde. So A is going to be a diol, and then pick an acid. Now I have a molecule where I only have one functional group, the ketone, that's able to react with an organometallic. So I have to add these 3 carbons. And then, so we add our Grignard reagent. I always default to Grignards, but if you want to make it an organolithium or something, that's fine too. And then H plus, and that'll give us our product. As a general rule, you want to leave your protecting group on for as long as possible before you try to take it off. So basically, we shouldn't take the protected group off until like F, because we're going to keep it on for as long as possible to make sure that aldehyde doesn't react, and then take it off right before we want to use that functional group for something. So let's just assume here that we're going to use like water and like tosic acid to remove our acetal. So what is that going to make E? Right, so E would be all of this, right? But the aldehyde's protected. That makes sense? Right, last thing we're going to do is take off the protecting group. So that means the step before we take off the protecting group is all of this product. My acetal got a little scrunch there, but it's fine. So how can I turn this alcohol into a double bond? So, 2 ways to do this, right? One of which uses strong acid, which your acetal is not going to be a huge fan of. The other one uses and that last one's a period because always use an abbreviation for the bottom part. So that's a period. It's a dot. There you go. There is an O though for your KMNO4 answer. I will at least give you the O. This little hangman's your grade. Like each little dude is just like now the best any of you can do is a B. I'm sorry. Uh, oh man, someone just came in and saved you. Pocl3. Someone who I assume is still in their PJs and like they've only been up for 10 minutes. It's just like I got this. So what's the next part? So it's POCl3 and what? Pyridine. You were saved. And she has her camera on, and I can see not in her PJs. So like she's got her stuff together now. This is good. All right. So POCl3 impurity. Right. The other way you know how to do this is like sulfuric acid or phosphoric acid and heat, but you don't really want to throw a really strong acid in with your acetal, since your acetals fall apart when they're around really strong acid. So, how can we turn our aldehyde into a cis double bond? It's literally all we've done. Yep. Triphenylphosphine, and then, right, so you can see this carbon here is the carbon from our carbonyl, right? So then we are adding all of this. So this carbon right here, we'll make it red. That carbon right there, that's the carbon that's bonded to the phosphorus. That makes sense? So that's the carbon that replaces the oxygen. So we're gonna have, right, so that carbon is right there. Reasonable? Okay. So we left off, we were talking about protecting groups, and we got into silyl ethers, right? The protecting groups for alcohols. So that is, you've got some carbon chain, and you've replaced the H on the alcohol with a silicon, right? So you've traded that proton that can act as an acid for a silicon that is pretty resistant to base. These are not, silyl ethers are not reactive to most acidic and basic conditions. So this oxygen silicon bond is the same bond that makes up glass. So you can think about it as you basically just put a teeny tiny molecular size piece of glass on your molecule, right? Anything that basically doesn't melt your flask isn't going to break that bond, right? So you basically replace something reactive with a little piece of glass. It's not going to do anything, right? So there are a bunch of different versions of silyl ethers depending on what the R group on the silicon is. So they all have slightly different properties depending on how big those R groups are. And we're going to go through kind of the four kind of most common ones. So we're going to have, right, so we're going to have our generic one, right? And so if we make those silicons methyl groups, right, this is trimethyl, silyl, and it gets abbreviated TMS. So you can see your protecting group written out as O silicon with 3 methyl groups around it, or you can have it just be O TMS, right? So if you see TMS, you should think trimethylsilyl. The way that, like, almost all the silicon groups we're going to talk about get put on is they start out as being the silicon with a chloride on it. So if you see TMSCl, that is your silicon with its 3 methyl groups around it, and then it has a chlorine on it. So TMSCl is the precursor that we use to make a trimethylsilyl ether. So TMS is the smallest silyl group. It's the one that is easiest to put on, but it's the one that falls off the most. When I was in grad school, I used to have to put one of these on a carbon, and I had to spend, it was literally 3 steps, and I would spend the entire day from like 9 a.m. to 9 p.m. putting it on. And then if at the end of the day I wouldn't took it at MR, there was about a 20% chance that the silyl group would have fallen off at some point during the day, and I just had to restart my day all over again. Right? If I made the solution a little too acidic, it would fall off, and I just have to go, well, everything I did today was for naught. I've got to start over again. Why? Sigh. Right? So TMS groups are easy to put on, but they have a tendency to fall off. So as we get bigger carbon groups, the groups become a little bit harder to put on, but they stay on a little bit better. So you have a little bit more wiggle room. So there's TMS. Next size up is TES, triethyl silyl, abbreviated TES. So same thing, you may see it just written as OTES. And again, it gets put on starting from the same precursor, TESCl. Next size up is the first one that we're going to have that doesn't have all the same groups. Little line here. Be silicon. So we have 2 methyl groups and a tert-butyl. This is tert-butyl dimethyl silyl. Now, as if you got nothing out of this class, it is that you should have gotten that organic chemists are lazy. So this 99% of the time is abbreviated TBS. Every so often you'll see someone who's super fancy and they're like, oh no, this is TBDMS. And they put all the letters in there. But for the most part, we're like, yeah, we'll talk about the tert-butyl and you know what the rest of it is. So we're just going to call it TBS. Yeah, big yikes. So it's abbreviated TBS, same thing, comes from TBS chloride. In the silyl, in the protecting group world, this is kind of the Goldilocks spot. It's pretty easy to put on, but stays on through almost everything you throw at. All right. So this is kind of that sweet spot where it not too hard to put on, but stays on through everything. So this is a really commonly used protecting group, right? TMS and TES don't get used as much because they fall off too easy. TBS gets used a lot because it has that perfect balance of ease of putting it on, ease of taking it off. So this is when in doubt, TBS, right? So if you're doing if you were doing a synthesis problem, right? Again, they're multiple choice now, but if you had to like fill in something and you're like, I know I need a silyl protecting group, I don't know which one. TBS is like your safe bet that it'll probably work. Right. So the next one is the most stable. It's the hardest one to get off, but it's also the hardest one to put on. And that is triisopropyl silyl, or TIPS. And again, it could be O TIPS. And then TIPS chloride is one way that you can put this on. And we'll go over the exact react conditions of how you put them on in a sec. So tips, most stable, hardest to add, right? Then you have TBS, then you have TES, then you have TMS. It's least stable, easiest to add. So it kind of comes down to what kind of reaction am I doing? Like which one of these is going to be best? And like I'm giving you 4. I think I can think of like 6 more that get used, right? So depending on the size of the groups around the silicon, it changes their properties, right? But it's kind of like how stable do I need this to be? How long do I need it to stay on? Am I going to put my protecting group on in step 1 and then carry it through my synthesis for 20 steps? Well, I better make sure that I have a really stable protecting group because I'm going to do a whole bunch of different reactions. And, one reaction might be really basic, one might be really acidic. I better make sure I have a protecting group that can stay on for all those different things. But if it just needs to stay on for a step and then come right back off, you might be able to be like, oh, I can just put that on a TES group because I just need it on for a step or 2 and then I can take it right back off and it'll be fine. So it kind of depends, like you've got to plan to figure out which one's going to be best for you. So how do these go on? I kind of said that for all of them, we're going to have a chloride as our kind of precursor. So you're going to take your alcohol, you're going to add your chloride, and then you're going to add a base. So these are usually amine bases, like DMAP, your friend pyridine that keeps coming up over and over again, triethylamine, or imidazole. So for us, all of these bases are going to be interchangeable, right? So there's not going to be a right answer for what to pick for a given protecting group. You can use any of them. And that's just going to put your protecting group on. So you've got your alcohol, you've got your TBS chloride, and let's say DMAP. And it's going to put a TBS group on your alcohol. So just like a lot of other things, we're not doing anything to the carbon-oxygen bond. We're only interacting with the oxygen-hydrogen bond. So if my carbon-oxygen bond is chiral, I keep that chirality when I put on my protecting group, right? So if I had a chiral alcohol, and I'm like, I want to add TIPS chloride and imidazole. Right, I'm going to keep that chirality on my alcohol. I'm not doing anything to it. I'm not reacting with the carbon-oxygen bond. I'm reacting with the oxygen-hydrogen bond effectively. So when we had talked about protecting groups before, I said that you needed 2 things in a protecting group, right? It needed to be easy to put on and then easy to take off, all right? So these are pretty easy to put on. You take the silicon with a chloride on it, you add a base, and it adds to the alcohol. Easy enough, right? How do we get them back off? Right? Right? So I'm gonna break these into kind of 2 big categories. When R is methyl, when all the R's are methyl, so this only applies to TMS, right? All the R groups are methyl. All R is methyl. All R's are methyl. There we go. my high school biology teacher had a wall of quotes, and I said something wrong in class, and I was just like, I ain't no English spokesperson. That got put on the wall of quotes. Still true. I ain't no English spokesperson. They would throw me out of the English department super fast. Are you really a native speaker? I was like, born in West Virginia. Yeah, so you're not a native English speaker. Check. Okay, you need to go. Okay, sorry. Right. So if all the R groups are methyl, so if it's TMS, you can remove them. Right. So you can use HCl, TBAF, or HF. So TBAF tetrabutyl ammonium fluoride. Right. So for the most part, the way we end up removing silyl groups is we add fluorine. We add F minus. Right. Because TMS groups are so easy to get off, we can use acid to remove TMS groups, but anything that has more than just hydrogen, so TES and up, HCl doesn't work anymore. Right? So TES and bigger, you can only use TBAF and or HF. So TBAF is the kinder, gentler source of F minus, right? TBAF is pretty benign. You add it, and what ends up happening is silicon's second favorite atom to be bonded to is oxygen. Its favorite atom to be bonded to is fluorine. So we add F minus, and silicon basically is the meme where the guy's looking at the girl in the red dress over his shoulder. It's like, ooh, fluoride, how you doing? And like dumps oxygen and makes a bond to fluorine, right? We're super lucky that it works out like that, because if not, we have no good ways to protect alcohols. So we got lucky that silicon's like, I like oxygen, but I really like fluorine, right? So TBAF is pretty benign, relatively safe, fine. HF is super scary. It's the only thing I used in grad school that like I was like, whew, this is super dangerous. And I used phosgene, which is nerve agent. HF melts your bones from the inside. You get it on yourself and it just dissolves your bones, and like your finger will like shrivel off because the bone melts from the inside.
The question was how much HF to melt a human body. Students scare me.
Wow, how much does it take to melt an entire human body's worth of bones? I'm not sure, Dexter. But if on the news if on the news someone has melted an entire human body, I will be sending them your way. All right, right. This is when I stopped watching Breaking Bad. Is like the second episode of Breaking Bad. They went to a high school chemistry locker and pulled out like jugs of HF, and I was like, no, that's not happening. I'm sorry, I'm done here. Um, yes, so there was probably 10 years ago now. A woman was cheating on her husband with like a guy at her research lab, and so they came with a plan to kill her husband, and they just kept ordering extra sulfuric acid, and they just filled a 55-gallon drum with sulfuric acid, killed him, and put him in the drum. And when they found him, he got caught at the waist, so there was no like upper half because they put him in head first, but there was like feet still. Yeah, just get a divorce. It's easier, people. Like so. when I was in grad school, if you get HF on yourself, there's this paste called calcium gluconate you're supposed to smear on yourself to sequester the fluorine so you keep your bones. And this guy comes running up to my floor. He's like, "Hey, do you guys have any calcium gluconate?" And I'm like, "Why?" He's like, "No, we not that I know of." And he was like, "Oh, someone did," and just like took off. And I was like, "Oh, awesome, great." I saw no stumpy people. But if you want to like not be able to eat your lunch, just like Google like HF burns. So HF is how you etch glass. So if you ever seen like etched glass that's like etched, they use HF. So when you use it in a lab, you often have to use plastic flasks because it actually will eat your flask and etch the inside of your flask or just eat through your flask. T bath, good. HF, bad. HF, scary. T bath, it's fine. And so there you go. So you put on your protecting group, you carry it through for a while. Then at the end, you add fluoride. It takes your protecting group off, and then you can do other stuff, right? So, for example, we could.
The question was, how do you know which protecting group to pick when you're doing a synthesis?
Because you're going to be doing like multiple choice stuff, like you're going to like see what the protecting group is and you want to pick it. For the most part, like I said, you kind of default to TBS or TIPS. Um, but like, there's not like, I'm not, if you were like writing them out and I didn't show you what the protecting group was and you picked like TES and you carried it through, I'd be like, fine. Like, that's what you know. But like, practically, usually use TBS and TIPS when you have to do more steps and TMS and TES if you have to do less steps. But there's not like a magic number where it's like 5 or 10 or whatever. Sometimes you like pick your protecting group and you do your steps and then it falls off and then you're like, well, I guess I got to start over again and like do this differently next time. So some of it's trial and error. All right, so where would you like to begin here? C? So what's C? Missed it by that much. You should put the protecting group on first, right? I'm making a Grignard reagent, so I can't have a Grignard reagent and an alcohol in the same molecule. So I need to make sure that I put the protecting group on first before I try to make the Grignard reagent, right? So that's going to be the first thing you do is I'm going to put on the protecting group. And I'm going to put on TBS chloride. And yeah, sure, we can use, I don't know why I put a P there. So I was thinking DMAP, TBS, and DMAP. All right, so that's going to give us our protecting group. Nope. Got ahead of myself. Sorry. So excited. How do I make a Grignard reagent? Just use magnesium metal. Just Mg. I like to put a little zero up there to remind you that it's in the zero oxidation state, that it's just a metal. All right. So we look at D, E, and F. The tricky part here is I have this ether, right? There's no way that you like can add a Grignard reagent to something and have it spit out an ether. But how do you know how to make ethers? So if you have a double bond, you can add sulfuric acid to it and your what's it called? In your alcohol, or you can use iron trifluoroacid, not iron, sorry, mercury trifluoroacetate and an alcohol, Or you can do a Williamson ether synthesis, where you have an alcohol that you treat with a base and you add an alkyl halide to, right? Well, we know that if we add a Grignard reagent to something, we often make an alcohol, right? So it makes sense that we want to use a Williamson ether synthesis because we know that we can get to that alcohol starting material for that reaction by adding a Grignard reagent to an aldehyde or a ketone. Does my logic make sense? So sometimes you gotta look at it and go like, how many ways do I know how to make an ether? Okay, I can think of 3 off the top of my head real quick. Which one of those can I actually make the starting material for in the number of steps I'm given? It's like, well, Williamson ether synthesis starts with an alcohol, and adding Grignard reagents to things makes alcohols. So I bet you that's how I'm going to make my ether. So you can look at E and say E is going to be everything in that given structure after F minus the carbon chain of the ether. That make sense? So do you guys remember the base you need for a Williamson ether synthesis? Usually get it with like sodium hydride. And then I'm adding 2 carbons to that oxygen. Right? 1, 2. So I'm just going to need 2 carbons and a halide. How do what am I adding my Grignard reagent to? Right? This is what I'm adding right here. So I need to have the isopropyl and then the carbonyl group, right? So this carbon right here is that carbon right there, right? I've got 1, 2, 3, 1, 2, 3, and that's what I'm adding, right? And then I have your then H plus. So now I take off my TBS group. It's bigger than methyls, then there's all methyls. So I need to use one of my fluoride sources. I'm still scared of HF, so I'm just gonna put down T-bath, like show HF some respect. Don't wanna like get angry at me. I like my bones. Uh, bones are overrated. You ever see the Family Guy where Peter gets a genie and someone says they're gonna break every bone in your body, and he goes, "I wish I had no bones," and just turns into like a a pile of like skin and stuff. Bones not overrated, right? And now, how do I turn this lovely primary alcohol into an aldehyde? Somehow. PCC? Yes, indeed. PCC. Right? So I expect you to know the abbreviations and I expect you to know the structures for the silo protecting groups because I am a bad person. So, like, what if I, were to give you something like this where you have that, and then I only give you like abbreviations as like the choice for the reagent, right? If I give you like, oh, TES, TMS, TBS, TIPS chloride, right? I give you all of those. So you've got to be able to look at the protecting group and say, okay, that is a tips group. So then when you have like your little pull down menu of choices of like, what is this going to be? You actually can know that I need to have tips chloride and let's say imidazole to protect my, well, again, because I'm a bad person, I would do a better job of making the problem so you had never got what the abbreviation was. Right, so make sure that you know both so that if I just give you the abbreviation and then the structure as like options, you know what the structure, you know how to, which ones match to what, right? That you're not like, oh, I don't want to draw a tips group and then you say like, oh, it's TBS chloride. That doesn't get you to the same place. So just make sure you know all that stuff. How am I going to make my double bond in one step? Right, I can do a Wittig reaction. So I want to talk real quick about the oxidation of aldehydes. Great, so basically turning aldehydes into carboxylic acids. So, right, we can take an aldehyde and we can do the sodium dichromate oxidation. And that can turn your aldehyde into a carboxylic acid. I don't have it in the slide. I should probably add it. You can also do it with KMNO4 as well. Right. And these two, if you think about what's going on, make sense, right? So we're just starting with an aldehyde turning into carboxylic acid. These two reagents both turn primary alcohols into carboxylic acids, right? So if you think about how that works, right? So we've got our primary alcohol. If you add KMNO4, right, you end up making a carboxylic acid, right? We remember this from the alcohol section. What's the first thing that the KMNO4 does? It turns that primary alcohol into an aldehyde, and then it oxidizes the aldehyde to the acid. So we can just start from the aldehyde and tell the reagent to pick up from where it would normally, hey, instead of having to do the work to turn the alcohol into an aldehyde, I'm giving you the aldehyde. You have less work to do making an acid now, right? So those reagents that are going from primary alcohol to carboxylic acid also can just go from aldehyde to carboxylic acid. The other reagent, a new reagent for doing this, is silver oxide, and there usually has to be water around. And this will turn your carboxylic acid, sorry, your aldehyde into a carboxylic acid. What's neat about this is that the byproduct of this reaction is you just make silver metal. This reaction is called the Tollens Test. So we may have done this or done some, you may have seen it as part of the Organic 1 like functional group determination lab. And right, this was back in the day when we used to like taste stuff to see if it like tasted like we had made the right thing. That tastes like what I want. Why do I feel funny? right? If you want to know you had an aldehyde, we didn't have NMRs and IRs, right? You had to actually do chemical tests to see, like, hey, do I have this functional group? I'll know if when I run this Tollens test, if I see a bunch of silver played out onto my flask. All right. So, all right. So if you have, and it never shows up great like on these projectors. If you have like a new flask, right? It works best with a new flask. If you run the Tollens test, it will put a small thin layer of silver all across the inside of that flask and basically turn that flask into a mirror. So like if you look at this, this is a great big like 2 liter flask, right? If you look really close, you can see the lights and the students in the class reflected in that flask. So if you use a really new flask, you just mirror out the whole thing. So that was how we used to be able to tell if we had aldehydes. We would do this test, and it would turn that aldehyde into a carboxylic acid and make a little silver mirror. We could go like, oh, cool, I have an aldehyde. Now I can go back and do my next step, right? Because I know I have the aldehyde now. Right? Now we use this reaction every so often as just a way to oxidize an aldehyde to a carboxylic acid. We don't use it to like test to see if we have an aldehyde anymore. It's more, this is another way to oxidize an aldehyde to a carboxylic acid. Someone in the chat was like, I've etched glass before. They are a braver human than I am. Right? So this just generally works. So you can just be like, oh, hey, got my aldehyde. I want to make a carboxylic acid. There you go. The nice thing about this is this is pretty selective. So like if you add KMNO4 to a molecule, right? KMNO4 does a ton of different stuff, right? It oxidizes double bonds. It oxidizes benzoylic positions. This silver oxide in water oxidizes one thing. It reacts with aldehydes and turns into carboxylic acids. So in a more complicated molecule, like if you had, right, this, and you wanted to turn it into that, if you use KMNO4, oops, there you go. You use KMNO4, KMNO4 could react at this carbon, it could react with these carbons, right? It would just be a mess. But using silver oxide and water, only going to react with the one spot. So that is the upside. It's more selective, and even compared to like the sodium dichromate, and sulfuric acid, right? You're not using as harsh conditions, right? You're not having to add sulfuric acid to make your reaction go. So the last reaction we have for ketones and aldehydes. Oops, I forgot it. Got an F. There we go. Try again. Is the Wolff-Kishner. Again, I might have to like put a little German on it. The Wolff-Kishner reduction. For old chemistry, like it's usually a pretty fair guess. It's like they were German or they were Russian. Like that's basically the gist, our realm of people. So the Wolff-Kishner lets us remove uh, ketones and aldehydes, making alkanes. So we can take our ketone and then turn it into an alkane where we remove the ketone and put a hydrogen on that carbon. This is a two-step process. First, we need to turn our ketone into a hydrazone. So this we know how to do, right? It's hydrazine and an acid, PPTS or toxic acid, will make the hydrazone. And then we can treat that with KOH and heat, and that will remove the hydrazone and make the alkane. So this will often get rolled into one arrow, right? Where you are going to just, in step 1 of the process, make the hydrazone. Oops. Right? And then step 2, you're going to add that KOH and heat. Right? So you just kind of roll it into like one arrow because you're just trying to get from that ketone to the alkane. You can also just start, right? It doesn't have to be starting the ketone, right? You can just start from the hydrazone, right, as your starting material, and then do the same thing, KOH and heat, and get to the same place. So you don't have to start with the ketone and be like, oh, I've got to make the ketone, make the hydrazone. You can just start with the hydrazone as well. I'm going to go over the mechanism, but I'm going to only go over the mechanism from the hydrazone. Since you already know how to make hydrozones, you don't need to see that whole like mechanism again. Right? So okay, we'll use our simple example here. KOH and heat makes our alkane. So the mechanism, you have your hydrazone, has 2 hydrogens on it, and then you have KOH. Right? I'm just gonna treat it as just hydroxide. It'll be easier. I don't really care about the K. So I'm gonna pull a hydrogen off that nitrogen and make a negative charge on our nitrogen. And generate water. Now at this point, we can have a resonance structure where we move that negative charge. So we can have a resonance arrow here. These electrons will come down, make a nitrogen-nitrogen double bond, and push electrons onto the carbon. So that's going to give us our carbanion. We can then protonate that carbanion from water, the water that we just generated. Can protonate that. And we remake hydroxide. So now I have nitrogen double bonded to nitrogen. I'm like 2/3 of the way to making nitrogen gas, right? So now our hydroxide removes this hydrogen. These electrons in the nitrogen-hydrogen bond come down to make a nitrogen-nitrogen triple bond. And then we break this nitrogen-carbon bond to again make another carbanion. So then we get to carbanion plus water plus N2 gas. The nitrogen gas is really what our driving force is, right? Nitrogen gas is very stable. So we're getting a whole bunch of energy from making nitrogen gas. And so that makes up for the fact that we're making this carbanion, right? So we're kind of balancing out our energies again. Stable N2 gas, less stable carbanion, they balance out energetically. Let the reaction go forward. And again, carbanion picks up a proton. Get our hydroxide back. So we get our alkane, right? We have both hydrogens on it. and we no longer have our, in this case, C double bond N. We no longer have our hydrazone. We've removed it as nitrogen gas. So reactions are all pretty straightforward, right? You're going to just look at your whatever compound, and wherever your, give myself space, wherever your carbonyl is, it's just going to go away. Right? N2H4 is just the other way to write hydrazine, right? It's the only way you can put together 2 nitrogens and 4 hydrogens, basically, is hydrazine. So we can just cheat and just use the chemical formula. Right? It doesn't matter if it's an aldehyde, right? It will go away. We'll get rid of the double bond, just so I don't have to worry about any craziness. Okay, we tried to get rid of the double bond, and my finger is too fat, so I just got rid of everything. Finger, destroyer of molecules. Right? And just like we saw, it doesn't matter if I start from, the hydrazine, or sorry, the hydrazone or the carbonyl. As long as you get to that hydrazone, you are just going to remove it and give yourself the alkane. So, pretty straightforward. But why, how would this come up? Why would you need to be like, hey, I had this carbonyl, now I don't want it there anymore? And kind of the first example I could come up with is, what if you were doing some sort of synthesis and you needed to make a longer carbon chain? So let's say you had this, and in the end, you wanted to end up with, in some, however many steps, this, where you no longer have an oxygen there, right? There's a number of different ways to do this, right? But one way you could do it, right, is you could start with your aldehyde and you could add a Grignard. I've got all the carbons that I wanted in my product, but I've got this extra oxygen hanging around, right? So what we could do is say, all right, well, I know if I turn this into a ketone, say using PCC, right, that I can use the Wolff-Kishner to then turn it into a CH2. So then I could make it a hydrazone. Then I could add potassium hydroxide and heat, and that will get me to what I wanted, right? So you can, use a carbonyl as like a handle to add some carbons, but then get rid of the oxygen later. This is probably not the most elegant way to make this molecule, but it's a way, right? So you could need the carbonyl to do something in your molecule, or to facilitate a reaction or a couple of steps, and then want to remove it later. It could be that you can buy a starting material, like something super cheap that's naturally available that has a carbonyl on it, but you don't want the carbonyl. You want everything else. So you could use the Wolff-Kishner to take off that carbonyl and then use the material for what you wanted it for. So there's a number of reasons that you would just be like, I don't want this carbonyl anymore. Seem good? All right.